Okay, so we'll get back to 8.3 here. We're on problem 1, and I did parts A and B in the last video. Let me show you part C. So we have a tank that's 8 meters long, 4 meters wide, and 2 meters high, and it contains kerosene with a density of 820 kilograms per cubic meter to a depth of 1.5 meters. So the tank is not completely full. In part C, we're going to find the hydrostatic force on one end of the tank. Okay, so whenever you're working with ends of a tank, that's where you're going to be integrating the problem. Okay, whenever you're working with the hydrostatic force on the top of the tank or the bottom of the tank, you're just going to be multiplying some numbers together. There's no integral problem that is. Okay, so well, let's see. I'm using this list of steps here. So I'm drawing a coordinate axes and choose a convenient origin. Okay, so we got this right at the center, and the bottom of the tank is sitting on the x-axis. Okay, the top of the fluid is at 1.5 meters. Okay, so then let's see. Now I'm going to have to get the width function that's going to go inside the integral. So again, here is the integral that I'm going to be using. By the way, because I'm in the SI system, okay, because of the units that are given here with its meters, kilograms per meter cubed, and I can know right away that my answer is going to be in terms of newtons. Okay. If the units were given in feet, which they're not, but if they were, the units for the force would be in pounds. Okay, so and that's one of the things that I mentioned in the last video. Like know early on if you're going to give an answer in terms of newtons or in pounds, that's going to be important. So. Anyway, we have rho times g. Okay, well, rho is the mass density. So the mass density is 820 kilograms per cubic meter. And then g, the acceleration due to gravity, that's 9.8. And so that's a constant. Those two numbers there can go outside my integral. And then let's see the bounds on the integral. If the base of the plate is at y equals c and the top of the plate, which has fluid against it, okay, the top of the plate is is 2 meters high, but there's no fluid touching the plate for that last half meter. Okay, so I'm going to be going from 0 to 1.5 on the integral. Now, if I go back to the drawing here, here's the line x equals 2. Okay, and I've centered this right at the origin. So the width all the way across the plate would be 2 times x. So here's, x is positive, x is negative. I got 2 times x, x is 2. 2 times 2 is 4. Okay, so the width all the way across the tank is 4 meters. Well, I already know that, right? Because they told me that. But I don't always have a tank that's nice vertical lines like in this problem. Like sometimes it's slanted or sometimes it's circular or whatever. So we'll see problems like that coming up here. But the width is 4. Okay, so W of y is 4, and then a minus y. Well, a is the top of the fluid. Okay, so the top of the fluid is at 1.5 meters, and 1.5 minus y, that would be a minus y, and then stick a dy at the end. By the way, all of the fluid force problems in this section, all of them are going to be in terms of y. Your setup. So if you have any setup in terms of x, I don't know what you're doing. Okay, so take that into account. Okay, and Now we'd have to find the value of this integral. Well, if I bring out a 4, 4 times 820 times 9.8, that's 32,144. And then the antiderivative of 1.5 minus y, that's 1.5y minus 1/2 y squared. And we're going from 0 to 1.5. So when I plug in these bounds here, when I plug in 0, I'll be subtracting 0, right? And let's see. I got 32,144 times 1.5 times 1.5 minus 1/2 times 1.5 squared. I'm getting 36,162 newtons. Okay, that's the hydrostatic force on one end of the tank. That'd be my answer there. Okay. So let's try another problem here. In problem 2, it says that a large vertical dam is in the shape of an isosceles trapezoid and has a height that is 30 meters and a width of 20 meters at its base and a width of 40 meters at the top. Okay. Find the force on the dam due to the hydrostatic pressure if the water level is 5 meters from the top of the dam. All right, so let's see. The first thing is I'm going to draw a picture, okay, of one end of the tank, okay? I've got a trapezoid. I've centered this at the origin. The base of the trapezoid is sitting right on the x-axis. So let's see. Here's the point 10, 0. Here's the point 20, 0. So I'm going from 20 to negative 20 on the x-axis. The width is 40 meters up at the top, right? And 20 meters at the base. So here's 10 and 10 make 20, okay? And the height is 30 meters. And by the way, since I'm working with meters, anything involving fluid force is going to be in terms of newtons when I give my answer, okay? So that'd be important. And I can know that right away here, okay? The water level is 5 meters from the top. Okay, so the water is 25 meters in the tank. And now we're going to have to know the width function, the width across. And notice how that kind of depends on where we're at here. You know, that the width would be changing. So the bottom of the tank is 20 meters. And the top of the tank is 40 meters, right? So it depends on where you're at to get the width across, okay? Well, so here's the point 10, 0. Here's the point 20, 30. And let's see, if when I draw a line there, the equation of that line is y equals 3x minus 30, okay? The slope of the line would be 3 because changing y over changing x, 30 minus 0 divided by 20 minus 10 is 10. So 30 divided by 10, that's 3. Okay. And if we use the point slope equation there, y minus y1 is 0 equals the slope 3 times x minus x1 is 10. Now if I solve that equation there for y equals 3x minus 30, that's how I'm getting that equation, that line there that I drew on the right. Now again, everything about the integral is going to be in terms of y. Okay, so I'm going to have to know what this equation is when it is solved for x. Okay, so if I solve this equation for x, let's add 30 and divide by 3. X is equal to 1/3 times the quantity y plus 30. Okay, now here's when x is positive, and here's when x is negative. Okay, so the total width across the tank would be where I take 2x, okay, using symmetry. So if I take x, you know, going from 0 to this spot here, and then double that, I get the width all the way across the tank. Well, 2x, that's 2 times 1/3 is 2/3 times y plus 30. Okay, And I think we're ready to set up our integral now. So let's see. I'm in the U.S. customary system, excuse me. I'm in the SI metric system, right? Because the units here are in meters. And so when I use this formula, I get rho times g. That's 1,000 times 9.8. The note here, rho is 1,000 kilograms per cubic meter. Anytime you're working with water, and a lot of these problems are going to be where the fluid is water. Okay, so take that into account. And then 2/3, that's a constant that can come out of the integral. So then the bounds on the integral, let's see, the bottom of the plate is at 0, and the top of the plate that's got fluid against it, that's got water against it, is 25. So I'm going from 0 to 25, right? Y equals 0 to y equals 25. And then a minus y, well, a is 25 meters, right? So let the top of the fluid be at y equals a, that's 25 meters. Then 25 minus y is the depth of the fluid at y. Okay, so 25 minus y, that's going to be inside the integral, and then times the width of y. W of y, I've already found that. That's 2/3 y plus 30. I've already factored out a 2/3 there. And so y plus 30 is going to be left inside the integral. Okay, or this setup is what we'd need there for the integral. Okay, so then from that, we're going to have, let's see, when I FOIL out this inner part there, y minus y, that's negative y squared. And then, let's see, 25y minus 30y, that's negative 5y. 25 times 30, that's 750. Okay? And then the next thing is I can integrate that function there. Okay, and so that's what I got right here. And then I can plug in the bounds. Well, when I plug in 0, I'll be subtracting 0. So then when I plug in 25, let me finish typing this in here. I got 19,600 divided by 3 times 750 times 25 minus 5 divided by 2 times 25 squared minus 1/3 times 25 cubed. Okay, and that's going to give me, let's see, I'm not getting the right answer. So where did I go wrong here? Oh, no. Oh, it's a minus 5/2. Sorry about that. So, so you got a minus 5/2, and there we go. Okay, so here's the answer that I'm getting. Okay, this is in newtons. So 78,263,888.89 newtons. That'd be the answer, and that's an approximation also. So I'm using the approximation sign here when I give the answer. By the way, you know, a lot of these problems, not a lot, but some of them are going to be given in terms of scientific notation, just because on some of them you'll have large numbers, you know, and so it's more convenient to see that using scientific notation than not. So 7.83 times 10 to the, let's see, should be 1, 2, 3, 4, 5, 6, 7. So 7.83 times 10 to the 7th newtons. That would also be that'd be the answer that you find in the book. Okay. I'm okay with you giving your answer in the standard form there, or it's scientific notation. Either way is fine though. Okay. So, and take into account like what the answer should kind of be, you know, like you've got a large vertical dam. Okay, so there's a lot of water on the side of this dam. Okay, so I can know right away that the fluid force on the side of the dam is going to be some big number. Okay, you know, I'd be kind of suspicious if I were getting like a, you know, some small number there. Okay. All right. When we do, we'll say I got two more problems using fluid force here. We'll do problem 3 and 4 in the next video, and we'll go ahead and stop right there.